Tom Salemi of Device Talks. Welcome back to Device Talks Tuesdays. Very happy to have you here for a really fascinating conversation. You can see the title right there, Designing Servo Gear Trains for Zero Compromise Reliability in Surgical Robotics. Very grateful to the folks at Harmonic Drive for putting together this conversation. And I'm sure you'll learn a lot. Thank you to everyone who's attending. And we'll get into the housekeeping. So we've got some tools for you to use. If you want to ask a question of our panelists, please use the Ask Question widget. That's a little text chat box there. You can send the questions. We'll get them over here. I will read them aloud so everyone will know what you're asking, and we'll get the answers directly to you. We have an opportunity for you to respond or react if you don't have questions. You can submit the emojis. We love the emojis. Love to know that you're out there and that you're enjoying the conversation. So if you hear something particularly insightful or just appreciated a point that was made, let the participants know, and just shoot a smiley face or thumbs up or whatever you'd like to let us know you're appreciating the conversation. And I'll be on the attendee chat box during a lot of this, just saying hello. Let us know where you're at. Let us know, I don't know what your weather is. We're getting a thunderstorm coming through northeast Massachusetts that came out of kind of nowhere. So the weird spring weather is in full force here in Amesbury, Massachusetts. If you're having any problems at all during the presentation, yes, there we are. Thank you for those emojis. Love to see those rise up the screen. You can do a few things. You can refresh the browser. That takes care of most of the problems. You should probably at this point just try to avoid trouble by closing all your other apps and browser tabs. We'd love to have your full focus on this conversation, and it also helps you preserve bandwidth and make sure you see everything you want to see. So that's always a smart thing to do. If you're still having trouble, you can do the click help in the top menu for the troubleshooting steps, but I always say just reach out to our excellent producer, Chad, through the Ask Question widget, and Chad will reach out to you directly and make sure you can hear and see everything you need to hear and see. Before we begin, very quickly, Device Talks, we have our amazing podcast. Go to Device Talks Podcast Network and any podcast player. Check out Device Talks Weekly or Women in MedTech or other great podcasts. You can also find them at devicetalks.com. And next week, we will be in Boston at the Boston Convention Exhibition Center, now the Thomas Menino Convention and Exhibition Center, on May 27th and 28th. We would love to see you there. If you are planning to be there but have not yet registered, connect with me on LinkedIn. We'd love to help you get there. We've got some codes for Device Talks participants. Happy to share that with you, but it'll be a great couple of days of MedTech conversations. I just had a pre-call before this webinar. We're going to talk about the state of the medtech industry in Massachusetts, and I think it's going to be a really interesting time. So I hope we'll see you at Device Talks Boston. Thank you to Harmonic Drive for putting together this presentation. As I said, really grateful to have these experts here online to present their information and to answer your questions. You can get your questions answered if you're watching live or even if you're watching on demand. If you're watching this on demand, and you have something that isn't quite clear, just use the Ask Question widget box, and that'll go directly to Harmonic Drive, and you'll get an answer. Probably a little more lag time, but if you're watching this live, but it's still a very helpful resource. So these are our presenters of the day. We've got Jim Leonard. He's the Vice President of Sales, Harmonic Drive. Kyle O'Connell. He's Mechanical Drive and Design Engineer, rather. Sorry, Kyle, of Harmonic Drive. And Richard Cocco, Regional Sales Manager, east of Harmonic Drive. So this is at the point where I stop talking and I hand the microphone over to the experts. Richard, I believe you are taking over from here, and then we'll take questions from the end at the end of the presentation. But folks, please don't wait to submit your questions. Submit them as they come to mind, so we know how many we have, and make sure they're being directed to the appropriate people. So Richard, take it away.
Sure. Thanks, Tom. Hello, everyone. Thank you for joining this webinar with my colleagues, Jim, Kyle, and myself. As many of you may already know, Harmonic Drive LLC delivers precision motion solutions built around high torque, compact strain wave gearing, and integrated actuation. So let's shift to the why this matters in medical systems. Medical applications don't just demand performance, They demand repeatability, safety, cleanliness, and predictable life under real-world operating conditions. With that context, today's presentation, Designing High Reliability Servo Gear Trains and Actuators for Medical Systems, will focus on the design choices that reduce risk and improve reliability from early architecture through verification and validation, ensuring precision and durability in medical device engineering. Introduction and medical system requirements. We will touch on unique demands of medical applications and why gear train and actuator selection is foundational. Unique demands of medical applications. Medical electromechanical systems operate under a set of constraints that are significantly more demanding than those found in general industrial automation. First, precision requirements are extreme. Many applications, such as surgical robots, radiation therapy, positioning, and diagnostic imaging, require repeatable motion accuracy at the micron or even submicron level. Small positioning errors that might be acceptable in a factory environment can directly impact diagnostic quality or patient safety in a medical context. Second, medical systems must operate quietly and smoothly. Acoustic noise, vibration, and torque ripple can affect patient comfort, interfere with imaging modalities like MRI or CT, and degrade force feedback performance in robotic surgery. Third, these systems are often required to operate in sealed, sterile, or sterilizable environments. This places severe constraints on lubrication choices, material selection, and heat dissipation, since routine maintenance or relubrication may be impossible once the system is deployed. Fourth, long service life, simply a cost consideration, but a clinical necessity. Medical devices frequently have service lifetimes measured in tens of thousands of hours and are subject to strict regulatory approval processes, making post-deployment design changes extremely costly. Finally, reliability expectations are unusually high because failures can interrupt critical procedures or take expensive equipment offline. These combined demands mean that design margins must be conservative, performance must remain stable over time, and degradation mechanisms must be well understood. As a result, the selection of servo gear trains and actuators is a foundational decision that strongly influences whether a medical system can meet its clinical, regulatory, and economic goals over its entire cycle. Why gear train and actuator selection is foundational. In high reliability medical systems, the choice of gear train and actuator architecture sets hard limits on achievable performance and reliability, regardless of how sophisticated the downstream control algorithms may be. Mechanical errors such as backlash, compliance, friction variation, and wear are transmitted directly to the output and cannot be fully eliminated in software. For example, backlash introduces dead zones and hysteresis that complicate force control and can destabilize impedance-based interaction with tissue in surgical robots. Similarly, time-varying friction and wear cause performance drift, increasing the burden on calibration and validation processes. Early design decisions also determine how easily a system can be analyzed, tested, and certified. Integrated servo actuators with well-characterized behavior reduce interface risks such as misalignment, tolerance stack-up, and thermal uncertainty, all of which can become latent reliability issues. From a program management perspective, poor actuator choices often lead to extended development timelines, repeated design iterations, and unexpected failures during verification testing. In contrast, selecting a gear and actuator technology inherently minimizes backlash, distributes load efficiently, and offers predictable life characteristics, simplifies both mechanical and control design. This is particularly important in regulated medical environments where demonstrating safety and effectiveness requires extensive documentation and testing. In short, gear train and actuator selection should be treated as a system-level architectural decision rather than a component-level optimization, because its impact propagates through the precision, reliability, validation effort, and long-term clinical performance. Key design challenges in medical servo systems. We will discuss gear train design challenges in medical environments, backlash sensitivity, and its system-level effects, actuator-level trade-offs such as torque density, thermal limits, and duty cycle, as well as benefits of integrated strain wave-based servo actuators. Gear train design challenges in medical environments. Designing gear trains for medical applications involve navigating several competing requirements that are often in tension with one another. One of the most critical trade-offs is between backlash and torsional stiffness. Conventional gear technologies such as spur or planetary gears can achieve high stiffness, but typically at the cost of measurable backlash, which degrades positioning accuracy and force control. Preloading techniques can reduce backlash, but they often increase friction, wear, and sensitivity to manufacturing tolerances. Wear and lubrication present another major challenge, particularly in sealed or sterile environments. Medical systems may operate for years without service access, meaning that lubricant breakdown or contamination can directly limit system life. This drives the need for gear architectures with low sliding contact and stable lubrication behavior. Material selection further complicates the problem. Gears may need to be corrosion resistant, compatible with cleaning agents, or compliant with biocompatibility standards, while still maintaining high fatigue strength. Surface treatments that are common in industrial gearboxes may not be acceptable in medical contexts. Together, these constraints make it difficult for traditional gear trains to deliver stable, high-precision performance over long lifetimes. Strain wave gear technology, which Harmonic Drive LLC manufactures, addresses many of these issues by providing near-zero backlash, distributed load sharing, and reduced wear mechanisms, making it particularly well-suited to the unique challenges of medical applications. Actuator-level trade-offs: torque density, thermal limits, and duty cycle. At the actuator level, medical system designers must balance competing requirements related to torque density, thermal performance, and operating duty cycle. High torque density is often required to achieve compact joint designs, particularly in robotic arms and imaging gantries, where space is highly constrained. However, increasing torque density typically increases thermal stress on the motor and surrounding components. In sealed medical environments, heat dissipation is limited, making thermal management a critical reliability concern. Duty cycle further complicates the picture. Imaging systems may require long periods of static holding torque with minimal motion, which stresses motor windings and magnets thermally over time. Surgical robots, by contrast, may experience intermittent high torque bursts combined with rapid reversals, which can accelerate fatigue and demagnetization if not properly managed. Sensor integration is another key challenge. High-resolution encoders and force sensors are essential for precision and safety, but they must be integrated in a way that maintains signal integrity and reliability under thermal and mechanical loads. Integrated servo actuators that combine motor, strain wave gear, and encoders into a single optimized unit help address these challenges by enabling holistic thermal design, reducing interface losses, and ensuring that torque, speed, and sensing capabilities are well matched to the application's duty cycle. Benefits of integrated strain wave-based servo actuators. Integrated servo actuators built around strain wave gear technology offer several advantages that directly address the design challenges of medical systems. By combining the motor, gear reduction, and encoder into a unified assembly, these actuators reduce the number of mechanical interfaces where misalignment, tolerance stack-up, or assembly errors can occur. This integration improves repeatability and simplifies system-level reliability analysis. From a thermal perspective, integrated designs allow the motor and gear to be optimized together, ensuring that heat generated under expected duty cycles can be managed effectively within a sealed housing. Structurally, the high reduction ratios achievable with strain wave gears enable smaller motors to deliver required output torque, reducing inertia, and improving dynamic response. Importantly, the near zero backlash characteristic of strain wave gears is preserved throughout the actuator and enhancing control performance without the need for complex compensation. For medical device manufacturers, integrated actuators can also reduce validation effort by providing a well-characterized subsystem with known life and performance data. This can shorten development timelines and reduce regulatory risk. Overall, integrated strain wave-based servo actuators shift complexity from the system integrator to the component level, where it can be more effectively engineered and controlled, resulting in higher reliability and more predictable performance in demanding medical applications. Speaking of higher reliability and more predictable performance, my colleague Kyle O'Connell will next talk about reliability engineering and control performance in the next section of slides. Kyle?
Thanks for that kind intro, Rich. So for my portion of the presentation, we're going to get into talking about some of the engineering factors that go into designing medical actuators. Specifically, we're going to talk about common failure modes, reliability advantages of strain wave technology, redundancy, fault tolerance, fail-safe design, life testing, validation, and some predictive approaches. So let's get into it. So we're going to start by discussing how failure modes inform design decisions for highly reliable medical servo systems. On the mechanical side, gear wear and fatigue are dominant concerns. In conventional gears, localized tooth contact and sliding motion can lead to progressive wear, which is going to increase the backlash and reduce the stiffness of your system over time. Lubrication breakdown is another frequent contributor, especially in sealed systems where lubricant degradation cannot be easily addressed through maintenance, like medical systems. On the electromechanical side, motor overheating can accelerate insulation aging, reduce your bearing life, and in some cases, it can even lead to demagnetization of your permanent magnets, which is going to permanently reduce torque capability. A lot of these failures are not the result of single overload events, but rather prolonged operation near thermal or mechanical limits, which is going to add up over time and cause these failures. This makes them difficult to diagnose or detect during short duration testing, so they can be kind of tricky. Additionally, interactions between mechanical and electrical subsystems can create coupled failure mechanisms, such as increased friction leading to higher current draw and additional heating in your system. In medical systems, these gradual degradation modes are particularly problematic because they can lead to subtle performance drift rather than abrupt failure. Designing with a clear understanding of these failure modes and how they happen allows engineers to incorporate appropriate margins and monitor the strategies, as well as architectural choices like strain wave gears that inherently reduce the likelihood and impact of wear-related degradation. Now we're going to get into why strain wave gears reduce that likelihood. They offer a few intrinsic reliability advantages that make them well-suited to medical applications. One of the most important is load sharing across multiple teeth at once. Unlike conventional gears where the load is concentrated on a small number of teeth, strain wave gears distribute that torque over multiple teeth in a range, a large contact area. They spread out the contact stress and it slows the wear progression. Additionally, the engagement mechanism involves minimal sliding between teeth, which is going to reduce friction and improve reliability stability over time. Another key advantage is the stability of backlash over the gear's life. Other gears will slowly wear out over time, which is going to increase the clearance between the teeth and lead to higher backlash. Harmonic drives, or strain wave gears, on the other hand, don't have a traditional backlash mechanism from clearance. So as they age, the performance is going to remain consistent. This predictability is critical for medical systems that must maintain their validated performance over many years. From a fatigue standpoint, cyclic strain experienced by the flex spline in a harmonic drive is well characterized, and it can be designed with ample margin and operating within our rated limits. We work with our medical customers to assure this is always the case. These characteristics lead to more gradual and predictable degradation long-term, which simplifies life prediction and validation. For system designers, this is going to mean fewer surprises on your end during long-term testing and field operation, and a much higher degree of confidence that the performance at the end of your system's life is going to meet those clinical requirements and help you operate the way you want to. The best way to ensure those critical requirements, though, is through robust testing and validation, both on the customer side and at Harmonic Drive. Life testing and validation are central to demonstrating the reliability of medical servo systems. Accelerated life testing is commonly used to expose components to elevated loads, temperatures, duty cycles, or reveal potential failure mechanisms within a more reasonable time frame. But it's essential that these tests accurately reflect real-world operating conditions, as unrealistic acceleration can produce failure modes that you're not actually going to see in real life. We work with our customers to approximate their load profile and the conditions of their system so that we can do this accelerated life testing and produce realistic conditions and failure modes. Thermal margin validation is particularly important for integrated actuators, where motor and gear temperatures are closely coupled. A failure of one is going to lead to a failure of another. End-of-life performance measurements, such as backlash, stiffness, and efficiency, provide valuable insight into how performance degrades over time and whether it remains within acceptable limits as you put more and more wear on the harmonic drive and the rest of your servo system. In some applications, predictive maintenance techniques may be feasible, using motor current, temperature, or vibration data to kind of infer the wear progression. While predictive maintenance is not always practical in sealed medical devices, designing components with predictable degradation behavior, like strain wave gears or harmonic drives, makes both the testing and interpretation of those results much more straightforward. Ultimately, robust validation builds confidence not only in the initial performance of a system, but in its long-term clinical reliability and viability. Now, we're going to move into the impact of mechanical design on control performance and how encoder placement, feedback architecture, and backlash and compliance compensation strategies are going to inform that design process. So, the impact of mechanical design on control performance. Mechanical design choices are going to have a direct and sometimes underappreciated impact on servo control performance in medical systems. Gear stiffness, damping, and the hysteresis of those gear systems influence achievable control loop bandwidth and your stability margins. High compliance or variable stiffness introduces phase lag into your system. This will limit how aggressively the system can be tuned, and it will be much easier for the system to become unstable and oscillate. In force-controlled applications, like surgical robotics, mechanical hysteresis can distort force measurements and degrade transparency. Predictable mechanical behavior is, therefore, essential for robust control design. Strain wave gears offer relatively constant torsional stiffness and minimal hysteresis across their operating range, which simplifies modeling and tuning. It allows the control engineers to focus on optimizing performance rather than compensating for unpredictable mechanical effects. Strain wave gears will also provide more consistency unit to unit for these mechanical characteristics, which is important for scalable manufacturing and scalable validation. By selecting gear and actuator technologies that provide stable, well-characterized mechanical behavior, designers can achieve higher precision and more reliable control performance with less tuning effort and lower risk of field issues, which is pretty important for medical systems. Encoder placement is a critical architectural decision in high-precision medical servo systems. You have a few options. Motor side encoders are going to be the simpler option and also the much more cost-effective option, providing high-resolution feedback of motor position and speed. But there's a drawback, which is they're not going to measure your output motion, and they cannot account for gear compliance or deflection under load. Load side encoders are kind of the other side of the equation. They're going to provide a direct measurement of your controlled variable, the output motion. It's going to improve your accuracy and robustness in the presence of mechanical compliance. Dual encoders is sort of the combination between those two options. You have an input encoder and one also on the load side. They enable advanced control strategies such as disturbance observers and improved fault detection. In medical applications where accuracy and safety are very important, the additional cost and complexity of load side or dual encoders is going to be justified. Integrated strain wave-based actuators frequently offer flexible encoder integration options, allowing designers to tailor their feedback architecture to your application needs. Careful consideration of encoder placement early on in the design process helps ensure that control performance, reliability, and validation requirements are all met, and it's going to avoid headaches later on with late-stage redesigns. So we absolutely encourage you to put that in early. Now, backlash and compliance compensation. Various control strategies exist to compensate for backlash and compliance, including feed-forward techniques, observer-based methods, and adaptive control. These approaches can improve performance in systems with conventional gear trains, but they're going to add a lot of complexity and can be sensitive to parameter drift or variation over time. In medical systems, where validation and long-term stability are important, again, reliance on software-only compensation can be risky. Changes in backlash due to wear or temperature can invalidate compensation models, leading to greater performance or instability. Or if you're using adaptive control, that's just much more complicated overall. So it's better to avoid it. That's why having strain wave gearing is a big advantage, because backlash elimination is baked into the mechanical system. Strain wave gears inherently provide near zero backlash. It's going to reduce the need for complex compensation or adaptive control. And it's going to make once again, your validation much easier. The mechanical first approach aligns well with regulatory expectations. It reduces reliance on adaptive algorithms. That's it for my section. So I'm going to hand things off to Jim to take us through a couple case studies. Thanks, everyone.
Thanks for that, Kyle. So yeah, I'm going to, in my part of the presentation, cover some medical system case studies, and I'll take a look at two of them. First, surgical robot joint actuator, and then the second case study, I'll look at imaging system positioning mechanisms. Okay, so as far as the surgical robot joint actuator, surgical robot joint actuators represent one of the most demanding medical applications for servo gear trains. These joints must deliver high torque in a compact envelope while maintaining zero or near zero backlash to support precise position and force control. Smooth motion and low friction are essential for accurate haptic feedback, which enables surgeons to sense tissue interaction. And additionally, joints are often located near the sterile field, requiring sealed designs that tolerate sterilization processes, or at least at a minimum prevent contamination. Strain wave-based integrated servo actuators are widely used in this context because they provide high reduction ratios, excellent torque density, and stable performance over time. Design trade-offs typically involve balancing stiffness against weight and managing thermal loads during prolonged procedures. Lessons learned from these systems emphasize the importance of integrated design, conservative thermal margins, and early collaboration between mechanical and control engineers to ensure that performance and reliability targets are met simultaneously. Okay, and then the next case study, surgical robot, whoops, check that. The next case study is imaging system positioning mechanisms. So imaging systems such as CT and MRI scanners rely on precise, smooth positioning mechanisms to ensure high-quality images. Motion irregularities, vibration, or acoustic noise can introduce artifacts that compromise diagnostic accuracy. These systems often require long periods of static holding torque, placing sustained thermal and mechanical loads on the actuators. Strain wave gears are well suited to this application due to their smooth, ripple-free motion and stable backlash characteristics. Integrated actuators simplify installation and alignment in large gantry systems, reducing assembly risk. Design trade-offs include managing heat dissipation in enclosed spaces and selecting materials compatible with electromagnetic environments, particularly in MRI systems. So experience from these applications highlights the value of predictable mechanical behavior and long-term stability, as even small performance changes can have outsized effects on quality on image quality over the system's operational life. So key takeaways and practical guidance. We'll concern ourselves with core lessons for designing reliable medical actuators and what engineers should do differently when they come in on Monday. So designing reliable medical actuators. Several consistent lessons emerge when designing servo gear trains and actuators for high reliability medical systems. First, reliability must be designed in from the beginning rather than added during validation. Architectural choices made early have the greatest impact on long-term performance. And second, mechanical and control co-design is essential. High-quality mechanics simply control and reduce validation burden, while well-designed control strategies can fully exploit mechanical advantages. Third, we want to look at long-term precision challenges. Small efficiencies and errors compound over time in high-precision systems, and marginal thermal or mechanical margins that seem acceptable initially can lead to significant degradation over years of operation. And then finally, predictable behavior is often more valuable than absolute peak performance. Technologies such as strain wave gears that offer stable, well-characterized performance over life provide a strong foundation for meeting clinical and regulatory requirements. And what engineers should do differently on Monday. From a practical standpoint, engineers working on medical systems can take several immediate actions to improve reliability outcomes. First, demand detailed life, wear, and thermal data from actuator and gear suppliers early in the design process, rather than relying solely on nominal ratings. Second, explicitly model thermal and mechanical margins under realistic duty cycles, including worst-case scenarios. Third, prioritize zero backlash or near zero backlash architectures to reduce control complexity and long-term drift. And fourth, involve control engineers early to ensure that mechanical choices align with achievable control performance. And finally, look for cross-domain lessons from aerospace and robotics, where conservative design and rigorous validation have long been standard practice. By applying these principles proactively, teams can reduce development risk, shorten validation timelines, and deliver more reliable medical systems. So the topics covered in this presentation are intended to provide a practical framework for thinking about reliability in medical servo systems rather than prescriptive solutions for every application. Each medical system has unique requirements, constraints, and risk profiles that must be considered holistically. Questions and discussion are encouraged, particularly around specific applications, load cases, or validation challenges. Sharing real-world experiences, both successes and failures, helps refine best practices and advances the state of the art. By continuing to focus on mechanical fundamentals, integrated design, and long-term performance, engineers can contribute to safer, more effective, and more reliable medical technologies that ultimately improve patient outcomes. And with that, thank you very much. I'm going to turn it back over to Tom.
Great. All right. Excellent presentation. We'll move on to the thank you, Harmonic Drive, for doing this, and thanks to our attendees for listening in. Now is the interactive part of our program where folks can ask questions of our panel of experts. So got some good questions in there so far, but we've got time probably to answer more. So folks, please get them in. First question here. Let's see. Thank you for the thumbs up. Yes, lots of emojis, applause, and hearts for our presenters. It was a great presentation. Question is, if strain wave gears are zero backlash, what's the real world limitation engineers still need to watch for? What's the real world limitation engineers still need to watch for? Not sure who, I'll just throw that one up in the air and let you folks jump for it.
I'll take a swing at that one.
All right.
First one, zero backlash. Doesn't mean perfectly rigid. In practice, the key limitation to manage is torsional compliance and hysteresis under load. So strain wave gears typically have very low backlash, but they still exhibit elastic windup. So that's torsional deflection under load, which can affect dynamic response and settling time. Also hysteresis, which is lost motion due to internal friction and elastic behavior. And that can show up in precision reversals of direction and torque ripple and stiffness nonlinearity, and depending on load and operating point. So the design takeaway is you still want high stiffness and predictable compliance, especially if you're doing force impedance control or high bandwidth positioning. And that's why mechanical and control co-design matters. You tune your control strategy around the gear's compliance behavior instead of assuming the gearbox is an ideal rigid element.
All right. Any
I think kind of
counterpoint,
similar
Tyler?
to what Jim said earlier. Oh, sorry about that.
No,
I was just
going to
going
say any
to chime in and
counterpoint.
say similar.
Yeah, go ahead. Yeah, go
Yeah,
ahead.
no,
Sorry.
just agreeing with it mostly. Like he said earlier in the presentation, it's better to have a predictable system than a peak performance system, and that's what we get with the predictable hysteresis and windup.
Fantastic. All right, let's see. Next question here. When should we use motor side encoders versus load side encoders, and when is dual encoder worth it? Is that you want to go first, Kyle, or do you want Jim to take the lead on that?
Yeah, sure. So, like I said earlier in the presentation, motor side encoder is when you just have basically your input position monitored. Output is when you're going to actually want to see how the load and the internal dynamics of the system may be changing. And output is when you're going to get the load monitoring. When you use dual is when you want to see particularly like if the load or the internal system is being modified. So if there's any discrepancy between your expected behavior, the dual output and input encoders are going to catch that. So I think that's sort of the ideal case to use both input and output, is if you want to monitor any unexpected changes.
Sounds good. Jim, anything to add, or should we move on to the next question?
No, I think Kyle hit it both in the presentation and just now.
Excellent. Okay, cool. Next question we've got from Ahad. Ahad says, great presentation, exclamation point. When harmonic drives are part of a drivetrain, what are the best ways to diagnose their failures and distinguish them from other drivetrain issues? For example, sound, torque, ripple, or something else. Okay, you open that to the floor.
Yeah, commonly you may hear some sound, but it being that it's a single stage reduction gear technology, we achieve gear reduction through one stage. So we don't have multiple stages such as spur gears or planetary gears where they're put into stages and to achieve like up to 160 to 1. We can do well over 160 to 1 in a single stage. So that tends to keep the noise level of our technology fairly low. You can tell by looking at the output of the unit if basically it may have gone into like a dedoidal, what we call a dedoidal state. That's where it's basically has hit a high torque situation and it essentially skips a tooth and it goes dedoidal. It's no longer where it should be. But the good news with sort of that situation is that you can essentially disassemble the unit and then reassemble it, and it's generally good to go again. It may see a decrease in the torque capability of it because it may have done some tooth damage at the top. So the only thing is it will continue to work, but you may see a diminished torque capacity at that point. That you could see like on an oscilloscope or something like that, where you're measuring the current of the actuator or the motor itself. Mm-hmm. So But the good news is, even if it does a dedoidal, skips a tooth, or it ratchets, it's generally still operational unless you do some really serious damage where you may cause the flex spline itself, that's the thin-walled flexible member, to actually buckle and crack.
Great. Go on to the next question. We've got a question here. What's the single most common reliability mistake you see in servo actuators used in medical systems? Not sure who wants to take a swing at that pitch.
I'll grab that one.
Okay.
The most common mistake is underestimating thermal reality, especially in sealed, low airflow environments. Engineers often size for peak torque and assume it's fine looking at it that way, but reliability failures come from operating near the thermal edge for long durations, insulation breakdown, bearing grease degradation over time, and magnet temperature limits being exceeded, and also drift in performance that fails accuracy requirements long before hard failure. So for medical systems, the right mindset is design around continuous thermal margin, not just around peak torque, and validate the worst case duty cycles, including holding torque, confirm heat paths, treat temperature as a reliability multiplier, and because higher temperatures accelerate multiple wear out mechanisms all at once. Okay.
Great. Go on to the next question. Anyone else want to add to that? Looks like we're all good. Okay. The next one, sorry. Reading the number, not the name, from I think Bella. What reference standard are used? Oops, sorry. What reference standard are used for reduced validation and risk? Thanks.
I think I can chime in here. We have pretty extensive documentation on our website. A lot of technical white pages and a catalog that goes through in depth the installation requirements and the rated limits, what you should and shouldn't do during operation. It's a pretty informative read. Maybe not short, but it's worthwhile to look through if you're considering going with strain wave technology.
And that's on anywhere in particular on your website? I could put the link in the attendee chat.
Yeah, I think.
Or you could do it too, I think, if you want to. Oops. All right. Did we lose Kyle's photo? It's Kyle. All right. Well, we'll move on to the next question. Next question here. And folks, we got a few more here lined up. Oh, there we go. Hey, Kyle.
Don't worry. I may have ejected myself.
I thought I did something. I'm like, what did I do to poor Kyle?
No, that was on me. Okay. But yeah, I'll send a link in the attendee chat too.
Yeah, that's a great idea. Okay, cool. Next question, throwing out to the group. How do you approach lubrication and wear when the actuator must be sealed or near sterile environments?
I'll take a stab at that.
All right.
Basically, the key is to treat lubrication as a life-limiting design element, not as an afterthought, especially in these sealed medical environments that we were just speaking about. Because of the highly sealed medical situation, there's very limited relubrication options. The good news is we do offer various types of harmonic drive grease, which are suitable for all types of temperature conditions, duty cycles, torque, speeds. We have our line of standard lubrication as well as extreme environmental conditions. So generally speaking, for most applications, our grease is meant to be pretty much, not needing to be relubricated inside the gear train. It's compatible. It's been proven compatible with all kinds of seals, all different materials, and generally meets sterilization constraints. It's, again, based on a long life stability. We've tried and tested many different lubricants over the many decades, and we have narrowed it down to these typical lubricants that are in our catalog. And as Kyle alluded to before, we do have a lot of data contained in our product catalogs, and usually we have it broken down by product on our website. So for each product, you can see a lot of data and curves and graphs and lubrication and things of that sort. So I would encourage anyone who's interested to check out our website and check out the catalog for each product or product of interest.
All right, perfect. All right, looks like we've got one more question here. Last chance for folks, if you want to get your question in, now's the time, live or on demand. If you're watching this on demand, remember you can still type in a question. It'll go right to Harmonic Drive. You'll get it answered. So you can still be part of your conversation. But the live folks, you've only got a minute, another couple of minutes. So question is, let's see, if you had to pick just a few tests to de-risk a strain wave-based actuator for medical use, what would they be? A few tests to de-risk a strain wave-based actuator for medical use. Oh, Jim, you want to take a swing?
Probably the most important one.
Okay.
Sorry, Jim, if you want to go ahead.
Go ahead. No, Kyle, go ahead.
I mean, the chief among them is life testing, accelerated life testing, which is like I mentioned earlier, where you're going to subject the unit to similar loads to where you expect to see an operation, but maybe at higher duty cycles or a bit more aggressive, and that's going to be our best case test in a reasonable time frame to see what's going to happen to the unit over its life. That also sort of incorporates thermal margin, and at the end of the testing, we'll be able to go through and look at specific values of the gear or actuator. We'll be able to see the backlash, torsional stiffness, its repeatability, and we're also going to be able to see how the noise vibration is, or the wear, or what potential failure modes might have happened based off of your operation. So I think, that's definitely the best test, and you should consider it anytime you're planning to integrate an actuator or harmonic drive into your system.
Great. Jim, any other suggestions?
No, I think he hit them all. Sensor integrity under real conditions. You want to be checking encoder stability versus temp. And in the EMI environment, cable routing, connector reliability, signal quality. These are the types of things that cause pain in the field. It's not just broke, but it no longer meets the precision requirements. So that's all I'd add to that.
Great. Rich, last word to you if you want to get in this final question. I think we'll be wrapping up after this. Anything to add, or are we?
Yeah, no, I think just add that to what Kyle and Jim said was another thing would be the thermal margin. Again, that's a critical thing given the sealed environment that these actuators are essentially working in, and consider a worst case duty cycle in the actual enclosure. Confirm steady state temperatures and the transient peaks in temperature as well. But yeah, exactly what Kyle and Jim mentioned earlier as well.
All right.
Yep.
Guys are a good team. All right, cool. Well, I think that concludes our presentation by Harmonic Drive. Gentlemen, thank you for your insights and thoughts today. We're really grateful.
Thanks for having us.
Thank you, Tom. Appreciate the invite.
Excellent. All right. And thanks, everyone, of course, for attending and participating in this episode of Device Talks Tuesdays. Thanks to our friends at Harmonic Drive for sponsoring this episode. Again, if you're watching this on demand, you can still ask questions. Make sure you type them in before I stop talking, or you can just rewind and type them in then. But we appreciate the participation of the Device Talks audience. You folks always bring your A game to these conversations. So I'm grateful. Thanks again to Harmonic Drive. Thanks again to our participants. And with that, we will be taking a break next week for Device Talks Boston. So perhaps we'll see you down there. Once again, if you'd like to join us there, connect with me on LinkedIn. Love to help you get to the show. Otherwise, we'll see you on our next Device Talks Tuesday, which will be the first week of June. Take care, everybody. Thanks for being part of Device Talks.